So today I'm going to do a very quick recap, but instead of on hashing, I think most of you should have known this already. Like we learned about open addressing in terms of linear probing and also other probing techniques such as quadratic probing. And we also learned about the double hashing, right? Which is quite fun. Anyone finds double hashing fun? No? Yeah, fun fact, I think I've told several times in the class, but my midterm paper last year was not double hashing, but rather on perfect hashing. So your hash table will map to another hash table. Okay, but as long as it follows the uniform hashing assumption, then the runtime should be easy to be predicted. Expected O1. Okay? So today instead, I will be covering more on amortization. Okay, and of course, there will be more hashing today. Okay, and that should be quite expected. Okay. So, amortized analysis. Let me show you with a very quick example here. Suppose this is your daily expense for 6 days in the first week of March. Okay, so you eat food for $5 a day. Assume like you eat, I don't know you can get $5 a day, but okay, so food $5 a day. And then on 3rd March is your girlfriend's birthday. This time you bought a $20 present. I don't know what you can get for $20, maybe a voucher or something. Then you eat, and then finally on 6th March, you go watch a movie with your girlfriend, $20. If I ask you what is your daily expense, what would you say? What is your daily expense for these 6 days? $10. Why $10? Because you're taking the average, right? It is unfair for me to say that my daily expense is $20 because it's too high of an estimate. Okay? And that is actually what we are doing right now. Most of the times, we are only taking the highest estimate, that is your ON, or ON squared, or ON cubed, those kind of stuff. Then we multiply it by the number of operations we have. In fact, that we know some operations are actually less. And if we have more of these less number of operations, right, then this would be too loose of an estimate. So, as what Soumya mentioned, sorry, this should be $20, I think, yeah. So as what Soumya mentioned, one of the obvious ways we can do is, from all of these expenses, we can total them up. So 5 plus 5 plus 20 plus 5 plus 5 plus 20, that will give us $60. Then you only have 6 days, so each day you spend roughly $10. Okay? What type of analysis do we use here? What's the name? Amortized, yeah, but what specific type of amortized analysis? There's a name for this. I'm not sure if it's introduced or not. Okay. So there are 3 types of amortized analysis. The first technique is from all of your expenses here, you are going to sum up and then you divide by the number of operations, that is your N. Okay? And this technique is what we call the aggregate analysis. Okay? Aggregate analysis means all of my costs here, I will going to sum up them. I'm going to sum them up and finally I will divide by how many operations I have to get a rough estimate of what is my average, average cost per operation. So each operation will bear roughly the same amount of cost for all N operations. This is what we call the aggregate method. Okay, so far any questions? Okay. Maybe before we continue, for those who just came, okay, so hi, I'm Jason Christopher, you can call me Jason. And maybe you can introduce yourselves first so I can take attendance for the lady and the other guy here. Ernest, okay. So this is Ernest. And you are? Oh, Amber. Amberlyn? Okay, Amberlyn. Okay. Okay, thank you. Okay. So far, any questions on aggregate analysis here? Aggregate method? No? Okay. Now, I will introduce you another type of method that is quite commonly used as well, which I think is not formally introduced in the lecture. So, some people will actually put a cap on each day, right? For example, like as an international student, I come here, I know that food here is expensive compared to Indonesia, okay? So I put a cap on my daily expense. What if I just spend like $10 a day? If I have more, then I can use it for some other days when I want to go to mall, to shop or something, okay? So in that case, I will put a cap on each of my daily expense. So I will deposit a certain amount each day. For example, for 1st March, I will allocate $10 just for that day. But turns out I only use $5, so the remaining $5 I will save them. Okay, I will save it into my balance. Second day, I put $10. I use 5, then the remaining 5, I will keep it to my balance. So that will be $10. Happens on the third day, it was like my girlfriend's birthday, although I don't have any girlfriend. Okay, so $30. I allocate $10 this day, right? But I still need $10 more. So I will take it from the amount that I have saved earlier. So this $10, I will use it with the $10 for that day to cover the $20. Then I repeat for the next few days. So it turns out, using this method, I can see that the minimum number of amount that I can deposit is $10 is enough to cover everything. If I put $9 here, then at the end, I might not have enough money for the birthday. I need to use credit card for this. Okay? But if I put like $11, then in the end, I will be saving much more. Okay, so depends on your operations. If your maximum worst case would just be $20, then this should be enough. Okay? And this method of allocating some money there, then you use some, you keep the remaining for other more expensive operation. This is what we call the accounting method. Okay? So the accounting method is when you try to deposit a certain number of operations, certain number of costs for each of this operation here. So you deposit a certain amount of costs. Even if you don't use, it's okay to store until the time that you have to use it for expensive operations. You can use everything that you have kept until now. Okay? So these are like two things. First of all, you sum up all the costs at the end of your month, then you divide by number of operations. Or second one is you try to increment it one by one. You allocate a certain amount of cost per day, then you divide, then you actually get, if it fits, then that will be a good upper bound. Okay, that is the accounting method. So far, any questions? Questions? Okay, no questions, then I need to discuss a bit on amortized costs and also expected costs, because we see that most of them are actually average, right? So what is the difference between amortized costs and expected costs? Anyone can answer. Amortized costs versus expected costs. Both of these are commonly referred to average cost, right? What's the difference?
One is deterministic, one is probabilistic.
Okay, one is deterministic, the other one is probabilistic. Yep, that is correct. Any other answers? Okay, let's discuss expected costs. When do we use expected costs? If we use something like random pivots or random stuff, random quick select, that time we will have an expected cost. Okay, or if you put like hashing with uniform hashing assumption, your expected cost is 0.1. But what is this expected? Your expected happens because of a probabilistic behavior. That is, it is more likely to actually have an even distribution compared to actually having an uneven worst case. So the likeliness is what we call the expected cost. For amortized costs, your average is actually done throughout calculating the cost per operations for every single operation, then you divide. Okay? So this part here is quite important. Amortized cost is a way to indicate such that every operation will bear approximately the same amount of cost. So you are trying to split the uneven cost for one operation. You are trying to divide it equally by the other preceding operations. Okay? As compared to the expected cost, which deals with probability and also average use case scenario for one single operation. Okay? So need to mark here that amortized cost, you need to consider like the sequence of operations that can happen now. Okay? In that case, because you can't say that, oh, I have one operation, what is the amortized, you can't really do much. But it happens that because you have like a number of operations, say M or O operations, in that case, you can take the average if you try to split the cost evenly. That is amortized cost. Okay, any questions? No? Okay. Then one of the fellow TAs also told me this quick analysis, right? You can think of worst case is like when you ask Prof. Seth on the midterm, okay? You ask Prof about the midterm materials, what will he say? What is in the midterm? Everything is in the midterm, right? So if you ask Prof on what is the midterm materials, then he will say everything. Okay? But if Prof will say like, oh, you know what's in the midterm? Actually, it's this part. You can focus on this. In that case, you can manage your time properly lah. Because there are some materials that actually not need, some that you actually need lah. Okay, so in that case you can think of how you can balance them together lah. Okay, any questions? No? Okay. No questions, then we are going to move on to today's tutorial problem. And first question, as with
You mentioned there are 3 methods.
yeah, okay. Good catch. The third method is the method that we rarely use because it's a bit more complicated. And the third method is called the potential method. Okay? If you recall from the previous method, accounting method here, you will allocate a deposit such that the amount of cost later in here, right, it will never overcharge. For potential method, you can think of it like a credit card. You can overcharge first. So your balance here may be negative, but in the end it will be 0, something like that. Okay, which is why it's a bit more confusing and it's a bit rarely. You will see this in 3230. For this tutorial, we are going to tackle with accounting method. Okay, so accounting method, it will not overcharge you. It will not like some sense of, in the perspective of your deposit itself, it will be much higher so that your balance will not be negative. But for potential, you can some sort of borrow the balance first so that it will be negative, then you cover it later. Okay, that is the potential method. How is that different? For example, if it happens that your girlfriend's birthday is in front, you can't say that I will allocate like $10 and then if girlfriend's birthday is on 1st March, right? Then if you allocate only $10, this will be negative, correct? In that case, that will count under potential method.
No, but how is it different from aggregate? Because
how is it different from aggregate? Aggregate is once you're finished for 1 month, you're going to sum up, you divide by the number of operations. For potential method, you store a deposit still, but then it is possible that your balance will be less than 0. For some cases, then you will cover up later. Okay, so you can think of it like some sort of, when you're planning your monthly balance, right? Sometimes you might be able to like just use first, and at the end you calculate what is your cost for 1 month. That's aggregate. So I don't care about how much I spend, as long as at the end I count, then I divide, I just want the statistic. That's aggregate. But for potential and accounting, it's like much more wiser in some sense because you can try to manage per day. But then like in accounting, you are quite wise in managing that you will never borrow from your credit card lah. But for potential method, it's okay for you to use credit card first, something like that. Okay. So aggregate, right? There won't be any deposit, but then at the end of the month you sum up, then you divide by n. That's aggregate. Okay. Any other questions? No? Okay. Okay, so first question is about hashing still. So last week we discussed about linear probing, and this week we are going to discuss more about quadratic probing. Although first question is still about linear probing here. So if you recall last week, this question was used for chaining, right? So this time we are going to use probing or open addressing method. But first of all, let us use the linear probing method here. So maybe we can do like some snake formation. Starting from the back this time. Okay? So maybe from get in. I have a 23 here. What is the modulo with 7? What's the remainder? 2, okay. So the remainder is 2. So we are going to place it at bucket 2. Okay, easy? Easy. Oops. Okay, next maybe to is it Y?
1.
Okay, this will be 1. So we are going to place at bucket 1. Then Amberlin? 0. Okay, so we are going to place at which bucket? We are going to place here at 0. Okay. Then others. 41? 41 is? What is the remainder divided by 7? 6, okay. Thank you to the left guy there. Okay. So yeah, this will be 6. Then you will place in this bucket. Because 41 divided by 7 is 5, remainder 6. So the remainder is 6 here. So we are going to place at bucket 6. Okay. Wangche, 43 divided by 7. What is the remainder? 1. Which bucket does it go to? 3? Why not 2? Why not 1? Yeah. Because we are doing open addressing with linear probing. So we are going to check for bucket 1 here. But bucket 1 there's a collision. So we are going to increment by 1. But there's also a collision. So we are going to add it by 1. Then we insert in position 3. Okay, clear on this? Clear? Okay. How about next? This will go to 4. Okay, this will go to 4. Next, Ife. This will go to 5. Is it 5? Okay, so you go to 1,
Yeah,
then you increment 1 by 1, then it will go to 5. But this is a duplicate item. Okay, so it depends on how we want our hash table to be. In the case that, for example, if I want my item not to have duplicates, then I drop. But in the case that if you want to store an item of duplicates, then of course it will go to 5. Okay, in this case, the solution recommends the dropping part. So this will be dropped. But okay, if we are going to store duplicates, then it will be 5 here. Okay, how about the next one? 25? Ping Chen?
4.
4?
Equals to 5.
Okay, so it will go to bucket 4, but bucket 4 has an item, so we are going to move to bucket 5. And hence this will be 25. Finally, Jia Hai, 63. 0?
But it's filled.
It's filled. So what do we do if it's filled? This will actually cause something called a table full exception. Okay? When your table is full, you can't insert any more item, then it will cause a table full exception. The only case that it will not cause is if you will implement table resizing. So once you see that it's full or nearly full, then in that case you can expand your table. That is called table resizing. Okay? Any questions? Easy, right? Okay. Then the front part people will have to handle with quadratics later. Okay? So linear probing, we are going to probe from I from 0 to m. That means for every like possible hash, possible buckets there. We're going to check for the next one. If there is an empty slot, we insert. That is linear probing. But what about quadratic probing? Quadratic probing, we are going to change this part. Instead of adding the I by 1, instead of adding it by I, we are going to add it by I squared. So we are going to move to position 1, position 4, position 9, then position 16, so on and so forth. So every time we increment, there will be a quadratic number being incremented. Okay? So consider this hash table with size 7 and same hash function, x modulo 7. We're going to insert the elements in the following order: 5, 12, 19, 26, and 2. Okay, only 5, but we have like 7 people in front, so let's see. I'm going to do linear probing. Okay, so Ferdi, 5 will go to bucket 5. Okay, yeah. Andrew?
5, but it's filled, so you go to 6.
Okay, 5 is filled, so we go to 6 because 6 is 5 plus 1. Okay, so we go to position plus 1. That will be 12. Next, Vegan. Okay, so 5 is filled, it should go to 0. Is it 0? So let's see. If we are doing quadratic probing here, where does it go to? 2. Okay. Why 2? Because 5 plus 4, right? 5 plus 4 is 9. 9 modulo 7 is 2. So we are going to move to position 2. So the technique here is you will check position 5, but 5 has an item inside. So we are going to move one step. So we are going to position 6. But 6 also has a person inside. So we are going to move to position plus 4 from the original position. So something like this. Okay, you are going to move 1, 2, 3, 4. Then we get at position 2. Then we insert. So this is quadratic probing, in the sense that we don't actually fill the 0 directly, but we move to 2. Okay, any questions? No? Okay. How about next? Jeremy, 26?
5, but it's
5, but it's filled. Okay, 5 is filled. So this part is tricky. Just now we plus 1, then we plus 4 to get here. So this will be.
Sorry, why are we adding 4 again? Like, I don't really get it.
Because previously, right, we add 1, and then if it's filled, then we add 2, right, to get the next second place.
Yeah.
Then we add 3, then we add 4. So in this case, we are going to add, but since it's quadratic probing, the numbers that we are adding is going to be squared. So we are going to move by adding 1, adding 4, adding 9, and adding 16, and 25, so on and so forth. Okay? So in this case, which position does it move?
We add 9.
Okay, we add 9, right? From 5, we add 9. Okay, so 5 plus 9, that is 14, right? 14 modulo 7 is 0. So we are going to move 9 positions from 5. It will look something like this. It's a bit ugly, but we move by 1, then we move by 4 to get here, then we move another by 9 from 5. So that will look something like this. Okay? So 5 plus 9 is 14, modulo 7 is 0. So it will fall under bucket 0. And that is where we place the item. Okay, so you will see that quadratic probing actually increases the randomness of placing the items, in the sense that it will reduce clustering. Okay? Because there's a possibility that there will be clustering if you use linear probing. Okay? For quadratic probing, if it's filled, then it will jump more gaps, so it will reduce the clustering. Okay? Any questions?
Why is clustering undesirable?
Why is clustering undesirable? Good question. If it happens that I have everything of 5, right, then we'll be like 5, 5, then this will be like more 5, 5, 5, 5, 5, something like this. Then to actually fill in, like, for example, I have like empty gaps here. Okay? If I want to fill in a 0, then I have to move this much to get to the empty slot. Okay? Or if I have another 6, then I have to move another much. So if I have a clustering part, right, then to actually get the empty slot, I have to traverse through the whole hash table. That's the worst case. If I implement quadratic probing, then I will jump much more faster, which is why it is easier to find a slot, given a more sparse hash table in some sense. If the empty slot is not just 1, then that will be much faster to get. Of course, expected. Okay. Now what about 2? Okay, Soumya, if I insert 2?
Goes to 2, but then 2 is filled, so it goes to 3.
Okay, so it goes to 2, but 2 is filled. So since we are starting from this 2, so we are going to move 1, hence we are going to put the 3. Okay? In this case, we are not following the previous sequence of 1, 4, 9, so on and so forth, because the hash value is not 5. But now we are starting with the hash value of 2. So plus 1, then we will get position 3, we insert 2. Okay, any questions? Questions? No? Okay. No questions then. Now given the previous hash table, we want to delete 2 elements. The elements that we are going to delete is 12 and 5, where we are going to delete 12 first before deleting 5. What does the final hash table look like? Okay, so maybe you can say what happens if we delete 12.
Oh, you're supposed to put deleted, right?
Yeah, so in this case, we see that 12 is equal to 5 modulo 7, right? But 5 here is not 12, so what do we do?
We advance to the next one.
We advance to the next one.
Go to the key.
Okay, so we see that the bucket here, bucket 5, the element there is 5, right? It's not 12. So we are going to move using quadratic probing, that is the plus 1, plus 4, plus 9, until we actually find 12. Now we found 12, what value do we substitute? Deleted. Is it deleted or null? Deleted. Why deleted? Why isn't it null?
The search can go on.
So the search can go correctly. What happens if I put a null inside? Anyone else? Null pointer exception? Okay, maybe. But given that this is Java, right? So anything that I don't fill in here might be null also. So what happens if I put a null instead? It won't find? 19 and 26, yeah. So if I put this as a null, right, that means my search algorithm here, when I probe, right, the terminating condition is once I probe, whenever I see a null, then that's the end already of my sequence, in some sense. Once I reach null, then that ends. So if I put this as null, then I go from, for example, 5, I see a null, that means it ends. So I'm cutting it off early if I put a null, which is why we have to set this as a tombstone value, or like a dummy value, that is called deleted. So that when I see here it is deleted, right, then I will move to the next ones if I want to search. Okay? If I put this as null, it is same thing as cutting things early. Because null is your terminating condition to actually check that, oh, this is the end of my sequence, of my probing sequence. Okay? Any questions? No? Okay. Now, last one, easy. What happens if I delete 5? Just deleted, okay? So if I delete 5, then this will just be deleted. Okay? Any questions? Questions? No? Okay. Okay. Now, this part is quite fun. Can you construct a case where quadratic probing fails to insert an element despite the table not being full? Yeah. What's your name, sorry?
Sarji.
Sarji, okay.
You can just, using the same table with x modulo 7, you can just keep this like 5, 12, 19, 26, 33, 40, 47, and so on.
Okay, so with the same table, the module 7. Yeah, module 7. Then what do I keep?
5, 12, 19, 26, 33,
Okay, the previous one, right?
47.
The 5, 12, and 26. Like this, yeah. Then?
Yeah. When you get to like 8, when you get to like the 8th one, it's gonna fail.
8, 1, this will fail. Yeah. Why does it fail?
Because if you write down the sequence of square numbers modulo 7, you get 0, 1, 4, 2, 2, 4, 1, 0, and then it repeats again.
Mm-hmm. Nice catch, okay. So, in that case, it will fail. So let's see. If I put something like, this will be 5, right? So 0, 1, 2, 3, 4, 5. Then 12, that will go here. Then 26, that will go to 2, right? Then 33, that will go to 0. Then the other one, that will go to 40. Is it 40? Yeah, 40. 40, that will go to 5 plus 16, 21. Okay, this will go here, but cannot. So I will go next again. Then you will add. What do you add there? It will fail.
Because
will it fail?
because the x square will be the same as the
I think
negative x square, so you
you have to replace 7 with like a non-prime number.
Mm-hmm. If I replace 7 with non-prime number, then the probing will get every element.
The table will not fail, I think.
Okay. Okay. Yep, that's actually a good catch here. Any other responses? Thank you very much, Sarji. Other possible cases? I might need to think on proving this part, but I actually proved for one case already. Yep,
I have a three table case, since the quadratic probing only ends if, let's say, you try 3 times and you fail. So if you have if the second and the third box already have an element, and then we try to put an element in the one index so in the center index.
Oh, center index, okay.
Yeah. So the new element is in the center. The right two have
Right
an
two.
element.
So this one has element lah. This one, the left one doesn't have.
Yes.
Okay.
And then we try to insert something into center.
Okay. Yep.
So like the first attempt it will be like 1 plus 1 times 1, 2. So it doesn't work. 1 plus 2 times 2 equals 5. Modulo 2 doesn't work. Then the third one will be 1 plus 3 times 3, 10 modulo 1. Also doesn't work. Then we ran out.
Then you do the pattern, then you see like 0, 1, 1, 1, something like that. Yeah. This is actually the solution that I prepared also. Okay. So this will look something like this. But in this case, for example, if my hash function will just be a general one that returns me just 0. Okay. Then in this case, I will never reach the empty part. Yeah, this one is similar to Ping Qian's, and that is the solution now. Any questions? No one is wondering why this is working. So, why did I say that I prepared this instead of the modulo 7 version? For optional ones, I will not run through much, but there's actually a mathematical proof behind this. Okay, you can look at this thing called Fermat's Little theorem that actually specifies for any integer, right, there is a multiple of 3. 3, 6, 9, 12, 16, 3, 6, 9, 12, 15, 18, module 3, that will be 0, right? So that will go to bucket 0. But anything that will be like something like 3k plus 1, 3k plus 2, then this will actually fall to the same bucket of 1. Okay? So this 3k part, it doesn't mean that our value, but rather this is actually the increment, the amount that we actually increment later on. Okay? Hence, we won't reach bucket 2, given that our hash function will only be at 0. Because when we increment, it will only fall under bucket 0 or bucket 1. Okay? You can see this under number theory. Okay? MA3265 number theory if you're interested. Anyways, okay, that'll be for question 1. Any questions? But it's optional. It's not covered in lecture anyways. Any questions? Basically, once you actually see a pattern, then that should work also. But in this case, just to make it better, because we are dealing with quadratics, right? We square them. And I'm not sure if there's like specific properties there, except for this one that specifies if my P here is 3, then if my A is actually like relatively prime to 3, right? That means if the greatest common divisor is 1, there's no common factor between both, then in this case, I can say that A raised to 3 minus 1, that's A squared, will be equal to 1. Okay? Which is why I take 3 as my P. So anything that is not a multiple of 3 will have this property. Hence, it will only go to bucket 1 later on. Okay? Questions? No? Okay. Okay, now let's go to the second question, which is more fun, I'd say. Suppose we follow these rules for implementation of an open addressing hash table, where n is the number of items in the hash table and m is the size of the hash table. Okay, so most likely we will say that your n will be less than or equal to your m. Okay, because you can't have n greater than m, right? Okay, so your number of items should not be greater than your size. Now these are the criteria for table resizing. If your n is equal to m, that means once your table reaches your capacity, then the table is quadrupled or resized to 4 times its size. Now if your n is less than m over 4, once it reaches like less than a quarter, then you are going to shrink your table into just half of its original size. Okay? So the questions here is, this part is a bit creative. What is the minimum number of insertions between 2 resize events? And what is the minimum number of deletions? Between 2 times we resize, what is the minimum number of insertions that can trigger double resizing? This part, a bit ambiguous, but it's quite fun if you can see which one is the minimum number of insertions and deletions. Anyone want to take a guess? I think deletions is easier than insertions first. Maybe we can discuss deletions first. Okay, Ping Xian?
Deletion is 1.
Deletions is 1, okay. Why is it 1?
Because after you insert, the table size is 4 times the number of elements.
Okay.
All the things is really, then you need the condition table from.
Okay, so once you insert, right? For example, I have like an almost filled table, then everything here is filled. Then once I insert this part, then this will be quadrupled, correct? So this will be quadrupled to 4 times. Then what will happen next?
Then you delete 1 element.
Okay, I will delete 1 element. If I delete this part,
Then n is less than the table size divided by 4.
okay, now your n is less than the table size, the new one, divided by 4, right?
Yeah.
So that will trigger a shrinking. Okay? Yeah, that is actually correct. So we have this one item that's like the crucial item. Suppose I have a nearly filled table. Once I insert 1 item there, then it will be resized to 4 times. Then if I simply remove this element, then I will get the n is less than 1/4 of my big size. So this will be shrink to 1/2 of its size. Okay? So 2 resizing events, the minimum number of deletions is just 1. Because although there are specific cases that there will be greater than 1, but still the lowest one we can get is just 1. Okay? Questions? Why is it 1? Any questions? Okay. Maybe for those who want to see. So suppose my table originally has 6 elements, then 5 is already filled. Okay. If I fill in the 6th one, then since my n is equal to my m, right, this will trigger a resize to 4 times. So now my n is 6, then my m is 24. If I delete this part, okay, then my m would be less than 24 divided by 4, is 6. So 5 is less than 6. So I will need to resize my m from 24 into 24 divided by 2, that is 12. And hence this would be just one deletion. Okay. Now the tricky part is, how about insertions? This part might be mixed opinions. What about insertions? You can think of like, my hint here is, you have a combination of table growing and also table shrinking, right? Okay. So can you think of whichever combination will have the minimum number of insertions? Is it when you grow first then shrink first then grow, or when you grow it grows again, or shrink then shrink again? Which one in the middle will cause the minimum number of insertions? It grows and grows again, okay. Okay, let's see if it grows and grows again, then what is the minimum number of insertions I should do? 3, yeah, 3 what? 3 insertions? In terms of M and N? In terms of M and N? Okay, so let's take this example, I think it's easier to see. So once I fill in this part, right, then there'll be, oh sorry, I think it should be the original example. Oopsie. Okay. So if I fill in this part, right, then now my M is 6. Then this will be my first growing part, right? Okay. Then what next? Then we shrink or we grow again. Just now you said grow again. If we shrink. Now I am concerned on like how many number of insertions would trigger this 2 times. If I shrink this, then there will be deletion, right? Once I put this, then if I shrink this, then there will be deletion. How about if I resize by insertions between the two of these? Just now we insert first, then we delete, right? So the delete is between the 2 resizing events. Our concern is in between the 2 resizing events part. So in this case, if we are going to take that it grows first, then it grows again, right? Then the amount that I have to add is as much as this part, right? Before it eventually grows back to 4 times. So this is equal to like saying, if my m is already this 4m, then there will be something like 3m over 4 for this new m. Okay? Now what about, is there a better way of saying this? Shrink and grow, okay. If I shrink then grow, how do I do that? Okay, so in this case, say my m is large here, then something like this. Okay, so if I shrink this from, initially there's like n is 6, then your m is 24, right? Then if I delete 1, this will be n is equal to 5, your m is equal to 24. Okay, hence what will happen? I will experience a table shrinking. Right? This will be a table shrinking. Now from this, how do I actually move to growing this again? I will need to add this part, right? 1, 2, 3, 4, 5, 6, 7. Correct? 7 is much less than adding this 3m over 4, correct? So in this case, yeah, this will be the minimum number of insertions part. So when I shrink first, then I grow, right? This will ensure that my table will be much smaller for it to trigger another growing event. Okay? So in this case, can anyone tell me what is the amount that I should add here? M over 2 plus 1. Yeah. Okay? When you take the m as like already the 2 times the original one. Okay? And hence this would be the minimum number of insertions. So you will only consider, you add these parts, the orange ones, you add them. That will be adding 6 from m divided by 2. Then you add 1 to actually fill in the one that you deleted just now. Okay? And this will trigger another growing event. So the minimum number of insertions you will get is m over 2 plus 1. Because as compared to growing the table twice, right? As compared to the minimum number of insertions to have 2 growing events, this will take 3m over 4 with the new size. But here, we only need m over 2 plus 1 with the new size here. So it will be much smaller. Okay? Any questions? Questions? Clear? Clear on this? Clear on this? Any questions? Yep. This will be a bit of a summary. Minimum number of insertions is when you shrink first, then you grow. Then minimum number of deletions is when you grow first, then you shrink. So it's a bit of an opposite. Okay? And it happens most in life. It's like parallel universe. In one universe, you have this version, then the other one, you have like the evil version. Okay? Questions? Now, have you all discussed table resizing in lectures? Yep, okay. What about the runtime? What is the runtime for table resizing? Let's discuss this first. M1 plus M2 plus. Okay, what is M1, M2?
The size of the old one and then
Okay, size of the old one plus the new one.
M2.
Okay, the M1, the new one. Then if you resize again, there will be the new one also. Okay. How about the amortized cost? If I'm doing resizing, right, of course at the end I will need a worst case operation to actually remake the table. I will create a new table, then assign each values. That would basically be this much operation. But I cannot say that all of my operations will be this much, right? Or else that means that using table resizing, my hash table becomes much slower. Where in fact, it's not that case. So what do you do here? What about the amortized cost of operation? For example, you are going to insert, resize. Insert, resize. What is the amortized cost for each insert and resizing operation?
How often will you do the resizing?
Good question. How often do we do resizing?
Depends on which we use.
It depends on the condition. Okay? For example, in this case, our condition is once your table is filled, then you are going to do a resize. Okay? But it will ultimately depend on your condition. Some people might want to do resizing after it reaches, say, m over 2 or m over 4. Why do we do so? Because it will be easier for us to actually get the expected place. If you are going to only do it once it's full, it's very hard to actually get that empty slot, which requires like linearly search for the hash table. So most of the times we actually resize when it's like m over 2 or m over 4. Okay, but ultimately it depends on your condition. How do you want to resize? Okay, but maybe let's take this condition first as an easier case. In this case, what is the amortized cost? N? ON for operation? For operation? ON for the everything? Yeah, amortized for each operation. What is the amortized? O1? So you have ON, O1. Any O log N here? Any O log N? No? Okay. Who says it's ON? ON? Yep.
By operation, do you mean resizing or like?
For each
just
insert
operation?
and resize operation. For each insert and resize.
Including resize.
Including insert. For each operation, not for the total operations. I'm asking for each. Amortized cost, yes. Okay. ON? Who says ON? ON? Who says O1? O1, O1, O1. Okay. So let's discuss here. Suppose my table will be something that looks like, let me just blank this first. Here's another one. It's easier to see. Okay. Suppose my table looks something like 1, 2, 3, 4. Okay, for easy searching. Then this one is filled, this one is filled, this one is filled. Okay, let's assume they are empty. Then I will insert into my hash table items like I will insert 1, I will insert 2, insert 3, insert 4, then other ones, of course. Okay. So what do I do? First of all, I insert 1 inside my hash table, that is one time, right? One time. Okay. Then I insert 2, also 1. I insert 3, 1. Then I insert 4. Insert 4. If I insert 4, right, this will be a resizing operation. Because once it's full, right, I will need to create a new table. that can contain all of my 1, 2, 3, 4 and also new items. In fact, this is 4 times up. Okay? So how do we actually account this? First of all, I can think of this as, this part is ON, then this part is O1, O1, O1. Okay? Using an aggregate analysis method, right, I can think of this as like, or instead of using the O operations, I think it's a bit more confusing. I can instead use like the numbers exactly.
N is going to be the sum. The sum of everything is going to be ON.
Yeah.
Yeah, so translate for 1.
Yeah.
Right?
Okay. Yeah. So in this case, right, putting item inside a hash table, I just need to hash it, then I place it, right? So technically saying like to hash it, then to place, there will be like 2 operations, then another 2 operations, 2 operations, and finally here, I need to hash it, that is 1 operation. Create another table, that is 1 operation. Then I have to move everything here, that is your n-1 operations for items here. Then I insert the last one. So that will look like 1 for hashing the item, 1 for actually creating the new table, n-1 to move everything from the old table to the new table, plus eventually 1 to put the item inside. So that will look something like 3 plus n-1, something like this. Okay. But how many n-1s do I have here? I have 2, 2, 2, 2, 2, all the way until I reach the condition where my table is almost full. So the maximum number of items here, there will be just n-1 items. Okay? So doing the aggregate method, I will get 2 times n-1, that's the cost of inserting n-1 items to my array, plus the cost to actually insert the last one, that is 3 plus n-1, something like this. Okay? So that will look something like 3n-1 plus 3, approximately equal to 3n. Okay? Make sense? Make sense? So this part, the 2n-1 is the cost to insert n-1 items until it's almost full. Then once I insert the last item, that's the last straw that broke the camel's back. Okay? The last straw here, that will take you 1 operation to convert this into the hash value, 1 operation to create the new table, n-1 operations to move everything from the old to the new one, and finally 1 operation to put itself. So this will be my 3 plus n-1. So combining this, I will get 3 times n-1 plus 3, that is equal to 3n. And this is the total cost to insert n items into my hash table. So 3n is for n items, so each item is 3 operation. Okay, so I can just store 3 operation per item. Hence this will be O1. This is called the aggregate method. Any questions? No questions? Okay. No questions then, how about the accounting method? Accounting method, right, it's actually hard to come up with a number. But most of the times if you use aggregate already, then you can get the number, then try accounting. Okay? So we know that we will only take 3 operations, right? Okay? So in this case, I can assign, for example, every time I insert, then I will store $3. Okay? So for example, day 1, day 2, day 3, day 4, this will be $3. Okay? I see that first time I will have $3. What do I use for? I will use $1 to actually hash the thing. Okay? To hash it into the 1, there will be $1. Then to actually put this inside the table, there will be another $1. So counting my savings is how many dollars? $1. Okay? Because I put $3, I use $2, so remaining $1. Okay? Okay? Now what about the next one? 2. Also the same, right? I will hash it, I'll store it, so that will take me $2. So remaining, I will add another $1 here. All the way until I reach 3, then now my savings will be $3. Okay? Coming to the last part, when I insert 4, okay, this part is like when your girlfriend's birthday lah. Okay, you have to buy some items for your girlfriend, of course. Okay, so in this case, you currently only allocate $3, but you need a lot of money for that. So you are going to, first of all, hash this, so that will be minus $1. Then create the other table, that will be minus $1. To move items from this table to the new table, I will utilize this $3. Okay, so actually to move this item to the new ones, then I will utilize the $3. And hence, finally, I will just need to use my last $1 to move my 4 inside. And that is the accounting method. Okay, so accounting one is I allocate a certain amount of money each time. Then, if I have excess, I store. For more expensive computation, that is when I resize. Okay. Although to be fair, I think the numbers here are a bit inaccurate, because if you want to resize another one, then this will not be enough. Okay, in that case you need to account for that also, which is why accounting method is actually more difficult to think of the exact number, but it's more useful in some sense. Any questions? Questions? No? I think I'm going a bit fast. Any questions? Okay, no questions, then we can move on. Let's move to question number 3 about union and intersection of sets. How would intersect and union be implemented for each of them? First of all, hash table with open addressing. Including the runtime. This part is difficult, let's say. Ideas. Okay. I want to intersect and union two hash tables. Two sets that are implemented with hash table with open addressing. So you can think of something like, if I have like say a set of 1, 3, 4, 5, 7, then I will have a hash table with just 1, 3, 4, 5, 7, something like that. Then another one, if I have like 2, 4, 6, 8, then I will have 2, 4, 6, 8. Then if I want to intersect and also union, how do I do so? But in the case I have like 2, 4, 6, 8, 10, right? Something like that. And then like if my hash table is only like modulo 6, then my 2 and 8, there will be open addressing also. So it can be moved to another ones. We can assume linear probing first for easier things. How can we implement this? Actually, you don't need to assume linear probing also can. Because the runtime doesn't depend on the probing. Maybe 1% for intersection, 1% for union. Ouch. Yes. Sudden silence. We just use a easier case. Say I have here a hash table, say table A. Then my set would be just 0, 1, 2, 3, 4. Then at 2 I have elements, say modulo 5. Right? Modulo 5, so that will be like say 12. Then here I will have like 31. Then this would be somewhere around 9. Okay. Then my second hash table, I will also have something similar, or even not similar also it's okay. Say something like this. So this will be from 0, 1, 2, 3, 4, 5, 6. This will be modulo 7. So I can have something like 9 modulo 7 that will be here, 12 modulo 7 that will be here. Then I will have something like 13 and finally 17. How do I find the intersection? We go through every single element in where? In one of the tables, okay. So we go through every single element in one of the tables. Then what do we do next?
Then you find the second table.
We find the second table, see if the element exists, okay. So for example, I will go through 31, then I will hash it with the second table's hash function, right? So I will get 31 modulo 7 that is 3. So I see that it doesn't exist. So then I will iterate the next one. Yep, that will also work in this case. Runtime? Oh, n? Oh. Any more specific runtime? Anyone can come up with a more specific runtime. Okay, so yeah, this solution will work. So in this case, right, if we have two tables, I can go through one table first. So this one I can depend lah. If I know the lengths of each hash table, then I can see which one has the less length. So they'll optimize it further. Okay, but it's okay, let's not consider this first. So if we are going to look through, for example, the first set, then for every key here, if there's an item, I'm going to check for the second set, see if the item is also there. If the item is there, then I'm going to add it into my intersection set, or else I won't be adding. Okay. So what is the runtime? Ta-da, ta-da. What's the runtime? Of length of the first table, okay. So something like, say let us use this terminology, okay. So suppose M is the size of the table, then N is the number of items inside. Okay, sounds fair? N is the number of items. So in this case, to go through the table, M, right? M, right? Because I will need to check each key if it's present or not. Okay. Even so, if it's not present, right, to actually traverse through to get the keys array, that will also take OM time also. Okay, so that will be something like OMA here. Okay, question?
Is this with or without SUH?
Let us assume with. Let us assume with. Because if it's not, then it should be already easy. This one should be OM. Yeah, with OM. Let's assume the Suha. Thank you very much for catching that. Nice. Okay, so we go through the table. That is OMA. Then what next? Okay, compare with the second table. How many comparisons do I make? NA comparisons. M, mic or nano? Nano, okay, nano. NA comparisons. What is the cost per comparison? O1? Is it O1? Any more specific than O1? Yeah, it's O1, expected. It's expected O1, yeah. To be precise, can anyone tell what is the runtime for open addressing? Precise one? Open addressing runtime? 1 over 1? Minus
1 minus
alpha.
alpha is n over s.
Yep. Okay, so that will be 1 over 1 minus alpha, where alpha is the load of your hash table, which is expected O1. Oh, alpha B, sorry, yeah, thank you. Yeah, this should be alpha B. Because we are going to take the load of B, okay? Then we are going to check the, we are going to compare with B here. We are going to see the elements, and the runtime is O of 1 over 1 minus alpha B, where alpha is the load of table B. Okay? And yep, this will actually be the solution. Okay? The reason why I write this because if I show the slides directly, I am afraid that you might be shocked. So better to check one by one. So yeah, this will be for intersection. So hash table with open addressing. For checking intersections, I will go through one of the set here. Okay, I will go through one of the set, and then for every item present, I'm going to check if B also has this item. Okay, and that should be quite obvious. Now suppose I have this hash table for A, then for every item in A, I'm going to find the item in B, but this time since I want to return a set also, so I will need to keep it in my result hash table. Every time I actually find the intersecting item, I will add it to my results. So if it matches, then I will add to my result hash table. Okay? So this runtime here, yep, Leah is correct here. So iterate through bins in one set A, then that will take MA. Okay, this will take MA. For every item in A, NA, nano A, look for the item in B. We are going to use this load B here, the load of B. And finally, to actually add to the result, then we are going to use this load of the result. Okay, so using open addressing, we are going to get the O's here. Hence, combining, right? This part, the looking for item and adding to result, is done for every single item in A, if it matches. Okay, so in the worst case, you might have a table that actually matches all of those, right? So worst case scenario, it will go down to this equation. Okay, where you are going to iterate through everything in A. And for every item in A, you're going to find your B and also add it to the result if it matches. Any questions? Yeah, this part is a bit confusing if you don't know what each symbol represents. Okay, but now you know, right? Okay, any questions? Now, what about union? For union, right, we don't actually have to keep a results table, but we just have to merge the two tables together. Okay, if there's an intersection, then don't do anything. But if there's no intersection, then you have to add. Okay, so in this case, I will take another take. For example, I will iterate through B. For each element in B, I'm going to add it to my set A. Okay, arbitrarily, both of them is okay. So doing this, iterating through B, I will need to take OMB time because I need to traverse through every single key in B to see if there's an item or not. And once I actually have the item, for every item there, I will need to add it to set A, given that there are no duplicates. Okay, if there's a duplicate, then you just need to drop, like the previous one. Okay, so that will still take O1 minus 1 minus O1 over 1 minus alpha A. Okay, so combining them, we're going to get this shorter version of an equation. Any questions? Suddenly silent. Okay. Questions? No? Okay. No questions, then maybe we can take a 5-minute break first before moving on to the second part of question 3. Okay, so maybe you can think of how we can implement chaining in the runtime. Should be easier than open addressing. Okay, 5 minutes break for those who want to go to toilet or drink. I think this tutorial is a bit more confusing, yeah. Or is it?
For the small a amount, interchangeable.
Yeah, it's interchangeable. In this case, we assume if like they are roughly equal, then yeah. But of course, right, I believe that although if your A is like less than B, then something that we can do is we add everything in A to B, right? Because that makes more sense. Okay, or we also depend on whoever has least number of size. So in that case, I'd say like if we are going to optimize that further, right, then we can get something similar to like a weighted union. But that will make this much more difficult to explain. So the current tutorial solution states this as randomly put.
Can I just ask, right? Like just now, the previous one, why is it two equations for the 1 over 1 minus alpha?
Oh, the which one?
Like just right before.
This one.
Yeah.
Yeah.
Like, why is it two?
This part.
Yeah.
Oh, this part is because I want to store it into my resulting table.
So how many? Oh, it's the other tables.
It's another table because I want to store the intersection. But if union, right, I can just merge one table to another if I want it to be mutable. If I don't want it to be mutable, right? If I want it to like create a new union, then in that case that will also be similar to this also. For the union. So I will need another plus or 1 minus alpha r. But this time I need to multiply it by, in the worst case, elements of NA plus NB combined. Because I need to add everything. Then that will be much worse for this. So a better one, if we want to optimize for runtime, is to add one set to another one. But if we don't want to optimize runtime, right, then we can run through both sets, and that is longer. But it will result to another immutable. It will result to a new table. Okay. 5 minutes break to.
So I think my code has of NK on the time complexity, but it has too much overhead, I think. Not really. So,
I think maybe like string operations are pretty much. My suggestion might be like instead of using like say
using the string as a
if
key,
you have
I
like
can just use the array as a key.
the strings are quite slow. That's actually what I did in my bottom line also. Strings are slow. So have to convert to another like thing will move faster. But depends on if you don't have much operations involving the string, then it's okay to store it as it is. Because to convert it, then that will take longer. Right?
Yeah.
So trade off.
So reference types can be used as keys.
If they are hashable, then they can. The important part is the hashable part. If you can implement like the hash code, then that will work. I think it's also in PS6, right? That if you use a certain hash code, then you also depends on whether you override the hash code or not. Okay, so one more student is not here. Sweet. Actually, if I don't use the screen, right, can y'all see? Like if I don't use the screen, is it visible? Or is it better to use the screen? Because the screeching part is a bit disturbing. Is it visible like this? Not the screen. Or do you all prefer the screen? Okay. Thank you. Okay, maybe we'll start first for the next question here. So we discussed about the union and intersection of sets using open addressing. Now what about if we use chaining instead? How would the runtime be? I hope you have your 5 minutes to think of a solution here. So how do we implement chaining to replace the open addressing method, and what would be the runtime? Union and intersect is chained here. So that will be like, for example, I have my first hash table, right? Some items, then this will point to like a linked list. Point to the linked list first, then another one will point to a linked list. Okay. Then I will have like the other hash table. So this will have like another linked list also, something like this. So what will be the runtime, for example? Okay, obviously then I will need to iterate through one of them. Okay, that will be very obvious. So runtime is for iterating. To check through each key, that will be O, M or N, micro or nano? Micro, yeah? Because you have to traverse through everything from 0 up to the size. Okay, so that will take OM. Those can see in the back, I think it's covered by monitor. Covered, yeah. Okay, so let me just cover. Okay, so this will take OM of A to traverse through each key in my A, right? Okay. Now, once I see that there's an item there, okay, what do I do for every item? Okay, hash code, yeah. Hash code, there is O1.
And then you check the bucket of D.
I will check in the, for example, this item, right? Then there will say 1, 2, 3, 4. Then I will take 1. I use the hash function of B. I will get, for example, 1 is here. Then what do I do to check for in the intersection?
That's 1 plus alpha.
Then there will be, do we use alpha here? Do we use alpha? No? Is it just O1? Is it just O1? What is the worst case for chaining? That will be, yeah, in this case it won't be, the worst case there will be ON of course for your B, then ON for A, because it can happen that if your chaining is all in one. But we can assume that this is a uniform hashing assumption here. So there will be O1 here, ON per M here. Okay, so in this case, right, I can say something like, for every item here, for every n in A, right, then I will have to check through the length of the corresponding bucket here. Okay, I have to traverse through the length of the corresponding bucket in my B. Okay, so if I want to be exact, right, although I can always think that it's O1 if I assume Suha, okay, that will be O1. But in this case, if I want to be exact, then I can say that, for example, if I take this as, say, the length of my set B, but for this bucket only, so it'll be something like, let's take this notation, something like I can say, for item K, the bucket here, in part B, something like this, okay? So the length of the linked list that corresponds to the key here in set B, okay? Or the length of the linked list here, okay? So that will be the length here. Then what else? If I do intersection, still have to do
NA.
NA or MA?
MA. Traverse the whole tree.
Okay, traverse the whole part MA. And then? Where do I store the result? I will need to create another table, right? And this table later on, I will also get another part here if I will use the linked list also. So in this case, my length of the key will be with respect to my result array. Okay? So the bucket here, right? I will take for each item in A, okay? For each item in A, I will have to check the length of the bucket that corresponds here, as well as the length of the bucket that corresponds to the results array in the worst case. Okay? Although, of course, if you can assume Suha, then this will be O1, O1. Okay? If you don't assume Suha, then this will be OND, OND. Or of whoever is the minimum later here. Okay? So we can say something like, let's just do a generalization. Say suppose the length of my bucket in B, that will be at length KB here. Then if my results table here, if I have another linked list, then this will be of length with respect to R, something like this. Okay? So in conclusion, my time here to intersect, that is similar to the previous one, OMA, plus for every item in A, I will need to check this one. Okay? The linked list for that bucket, and for bucket in B, and the linked list for the bucket in my R. Okay, so that will be something like len plus something like this. If I want to be exact lah. Later on, you can substitute this based on whether you want to assume it as Suha or whether you want to assume it as the worst case. Okay, but as general, it will look something like this. Any questions? Questions? No? Okay. Okay. What about union? What about union? Then the same method will also work, right? Okay. So I can take, for example, the previous one. Previously, I will iterate through every bucket in every item in B. I will add it to my A, right? So this one, we will also do something similar. We are going to check for every item in B that is OMB. Okay? For every item in B, I'm going to add my items into A. Okay, so that will be every item in B multiplied by multiplied by the length of A with respect to your set in A. Okay, so one bucket in A that corresponds to the key, then you take the length. Okay, and this will be if you want it to be exact. Okay, any questions? This one is general because you can change the length to whichever you want later on if you want to assume Suha or if you want to assume worst case. Okay, but for open addressing, since we know that that will be like the runtime line, so we can use the 1/1 minus alpha directly. Any questions on this? I think I'm a bit lost already. Questions? Going once? Going twice? Okay. If no questions, then we will move on to the fourth question. Fourth question is about amortization analysis also. So here we will have a binary counter. A binary counter is, for example, if you go to a plane, right, some of the stewardess, she will usually like hold a counter, then like count each of you, right? So one, something like that. Then it will recommend by 000, 001, 002, something like that. But now for a binary counter, we are going to increment by adding, like, for example, from 0, 1, 10, 11, 100, 101, something like that. So we are going to add 1 every time to our binary number. Now, increment will increase the counter by 1, and read will read the current value of the binary counter. Okay. Now, to make it clearer, suppose that we have a k-bit binary counter. Each bit is stored in an array of size k, where k denotes the kth bit. Okay, so we have a k here. That's the maximum size of our counter here. Okay. There's, for example, A110. This corresponds to, say, 011 in binary. And calling increment will yield 001. Yeah. So if you increment this, then you add 1 here. But it will carry to the next one. It will carry again until it reaches a 0. Then there's a time it will be 1. So you add here 1. This will be 0, 0, 1. So you flip all the way until you find the first 0. Then that will be your 1. Okay? That's how we do a binary addition. Then, suppose that the k-bit binary counter starts at 0, i.e. all the values in A is 0. Loose bound is, of course, whenever you want to flip right, we can assume that your operations here will actually be the number of times you have to flip the bits. Okay? If you have to flip everything, then that will be OK, something like that, right? Right, to flip all the bits, that will be OK. But then you have like n times you increment, then there will be ONK, because you have to flip everything. But in reality, right, most of the times you only flip the first bit. So it will be too loose of an estimate if I will take OK instead. So the question here is, what is the amortized time complexity of incrementing n times? Amortized time complexity. Amortization again. Anyone? This one's still an easy guess, I say. ON? For each? Oh. Okay, for all n times there will be ON. Okay. Who agrees it's ON? 1, 2, 3, 4, 5, 6. Okay. Any other solutions for those who don't agree it's ON? For all n times. For all n times.
I'm not super sure, but I was slowly calculating it out, and it seems to increase over time as n increases. So I'm guessing n log n.
N log n? Okay. N log
But
n.
I really have no other idea.
Good guess. Anyone agrees with n log n? 1 agree, okay? 2 only?
N log n amortize the total.
Hmm?
N log n is amortize the total.
Oh, sorry.
Total amortize. N log n, okay, that actually makes very much sense.
Okay, I think it's N.
N log n, okay, N log n, 3 people say N log n. It's like, there might be cases that you have to flip 2 bits, flip 3 bits, then another 2 bits, then 3 bits and 4 bits, right? Makes sense, N log n. Yes. So we have ON, then we have N log n. No one proposes N cube. No one? Okay. No one proposes K log K. Okay. So let's discuss the ON and ON log n first. Why ON?
Because the least significant bit is updated n times.
Uh-huh.
The second least significant bit is n over 3 times.
Okay.
The third least significant bit is n over 4 times.
Yep.
So you add it up, it goes to 2n. Converges to 2n.
Okay, if your k would be like going to infinite, then that would be about 2n. Yeah. How about Pingqian? Why n log n? Because of the increasing part, right? Yeah. Okay, so let's try to analyze this together. So the idea is, right, for example, initially I have 0. Then if I add 1, I will need to flip just this bit. Then after my second flip, that's the time I flip the second bit here. Okay? Then I go to third. Then after my fourth flip, then that's the time my second, my bit 2 will get flipped. So bit 0, bit 1, bit 2. Okay? I use the opposite notation as with the array because I think it's easier to see binary numbers. Okay? So when I add another one here, right, I will need to flip this, and this part gets flipped. So you will see that every 4 operations, this will be flipped. Okay? Moving forward later on, every 8 operations, this will be flipped. Moving forward later on, every 16 operations, then this will be flipped. Okay? So the amount that we flip, right, everyone agrees that every operation will flip the least significant bit. Everyone agrees this part will be flipped. Okay? Because this will be only 0, 1, 0, 1, 0, 1, 0, 1, right? Then this part will be 0, 0, 1, 1, 0, 0, 1, 1, 0, 0, 1, 1. So the amount of times that we actually flip is like 0, 0, flip, 1, 1, flip, 0, 0, flip, 1, 1, flip. So every 2 times. This part later on will be 0, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 1. Every 4 times we flip. Okay? So how many times do we flip, right? At most, if I have n operations here, bit 0, I will always flip it every time. I will flip it n times. Bit 1, I will flip it half of the times. Bit 2, I will flip it 1/4 of the times, 1/8 of the times, then 1/16, and so on and so forth. So if I combine all of these, I will get this part, n plus n over 2 plus n over 4, all the way until I have 2 raised to k minus 1, supposedly k minus 1. Okay? If I combine everything here, I know that this series will form my geometric progression, but this will still be less than an infinite series of 1/2, 1/4, 1/8, 1/16. And this infinite series is 1 plus half plus 1/4 plus 1/8, that is equal to 2. Okay? So the maximum number of bits I flip, if I will continue to all of my operations, right, there will be 2n. Any questions on this? So you will see that this one actually is similar to like some of the questions at the first tutorials, right? When it seems that there will be log n, right, but when you actually combine the half and 1/4, 1/8, that will actually combine just to 2n. That will be linear time. Okay, so this one it will be equal to 2n. Hence, at most for n operations, we will have like 2n amortized. Okay, so using the aggregate method, I know that for a very large n, I will get 2n. Then for every operation, I can divide by how many operations I have. So 2n is the total cost. I divide by n operations, I will get just 2 operations every time I flip. That is O1 for each operation. Then for total, yes, there will be ON. Any questions? This part is using the aggregate method. Now I will show you how to use the accounting method. For accounting method, you are going to deposit a certain amount of money. Okay? Can anyone tell me what do we deposit here? I think it's also in the slide. So we're going to deposit $2 for every operation. Okay? So initially I will have like my counter at 0. Then initially I'm broke, so I don't have many money inside my wallet. Okay? Then next morning NUS give me $2, but I will use one to flip my binary counter. So the other one I will put into my savings. Then the next time I want to flip, right, how many operations do I need? I need $2, right? Because I need to flip this one, I need to flip this. So that will make me $2. So do I add anything to my savings? No, because my $2 is used for these two. Okay? Then the next day, I will need to increment this again. I get $2, so I use 1, I keep 1. So my savings now increase to $2. Then the next day, right, I have to flip this. How many bits should I flip? 3. 1, 2, 3. But I only have $2. So I need to subtract from here. Okay? $2 is from this day allowance, $1 is from my savings. So now my savings will reduce by 1. Then I continue, something like this. Now I have like something like $3 because I already made 3 operations here, right? Then I will have $3. Now how many bits should I flip? 4. Okay, so 4, I will use $2. Then the $2, then I will have like $3 just now in my savings, so I need $2 from my savings to cover. So this is the accounting method. As you can see, my savings will never be negative. Although I'm broke, I'm not that broke. Okay? At most only $0 are still okay, right? Okay? So although I'm broke, not that broke. Yeah, that is the accounting method. Any questions? If the potential method, then when I broke, I'm actually going very, very broke. Okay? Until I have to beg lah. That's potential method. Questions? No? Okay. So yeah, average $2 per operation, or that is just a constant amount per operation. So you can think of amortize is that you can try to save money first for every operation. Then once you actually need to spend more, you can use your savings. Okay? Questions? No? Okay. No questions, then maybe for the last question of the day, we are going to discuss about your problem set 4, about scapegoat trees. Okay? So consider the scapegoat tree data structure that we have implemented. We assume that only insertions are performed on our scapegoat tree. In this question, we will use the amortized analysis to reason about the performance of inserts on scapegoat trees. So, suppose we are about to perform the rebuild operation on a node V. It's proving question here. So show that the amount of entries that must have been inserted after it was last rebuilt is omega size phi. So we want to actually prove that the minimum number of insertions such that it will be an unbalanced tree again after the last rebuild, that is just omega size phi. This part is a bit tricky. Anyone? Bonus participation for those who can answer. This part is tricky. Give like 2 minutes, 1 minute, you think? Now you can think of, maybe I can show a bit first. You can think of your scapegoat tree as something like, oops, okay. You can think of your scapegoat tree as something like this. Is it balanced? Scapegoat tree, not AVL, is it balanced? PS5, PS5, check balance, check balance. Is it balanced? Why not balanced? It's your left one, right? Your left one has 6 items. It's more than 2/3 of your whole size. Because your whole size is 8, so like 2/3 of 8 that is. Yeah, that is like about, I take the floor, that is 4 lah, something like that. If I take the floor. So it will be much greater. So in this case, what do? I will have to rebuild. Okay, I do a rebuild. Now when I do a rebuild, right, how many nodes should I insert so that it will rebuild again? That's the question. What is the minimum number of nodes that I need to insert so that it rebuilds? It tells us that actually we only need omega size phi, so the minimum number of nodes will depend on the size phi. But how do we prove it? Anyone wants to write on the board? Okay.
Very good done, I think.
Isn't that already unbalanced?
Sorry?
Yeah, that's already unbalanced.
This one is unbalanced, right? So once we balance it, it will look something like this.
Since it was last rebuilt. So that is like after rebuild.
So this one is like, when we reinitialize this, okay, this one is rebuilt.
So your question is, how many...
So from this state, right, from this state, how many insertions should I do minimally so that it will get rebuilt again?
What is B? Which node?
I think should be the root lah.
Go back to the...
I think this will go about the root lah, because if we rebuild, then that should be from this whole tree, right? Rebuild is from this whole tree.
Go to the what do you call this? The rebuild 3.
Mm-hmm. Yeah. Your V would now be this one, because it would be like rebuilt around this, right? Yeah, about.
That is being
Hmm?
It's the node that's being rebuilt.
The V would be okay. I'd say the V would be the root of your tree. Yes, the V would be the root of the tree, including the resulting tree. Any ideas? I think I've been spoiling like some items already just now. Okay, Wang Shen.
So after rebuild, you ideally get a perfectly balanced tree, right? So,
Ideally, perfectly balanced, yeah.
so ideally you would have like a 50-50 split on your left and right.
Mm-hmm.
So that means
Okay, yeah, 50-50, yeah.
just something like that.
Ideally, yeah.
That's ideal. And for one side to be unbalanced and to be the rebuild, you get to greater than 2/3, right?
Yeah.
So you need to minimally double the size of one side in order to get it to rebuild.
I guess in a sense. Double the size of which one? Double the size of one subtree.
Yeah, one side.
Double the size of one subtree is double.
So for this, it would be doubling node B, make it more than 2/3 the size of the entire tree to rebuild that side. Is that right?
Yeah, something like that. Yes. So you will have to increase like one of your subtrees, right? So it will be like more than 2/3. Yeah. So what is the number there? I think that should be easy to prove already. I can show you the easy solution first. Thank you very much, Wang Che, for showing. So now, suppose after rebuild, you will have an ideally balanced part. Okay? Then you want to add somewhere around one subtree, so that later on this subtree will be not balanced. Okay? When it becomes not balanced, right, then it should look something like this again, correct? So something like, initially it will look something like this. Then I will add everything to one subtree until it becomes the minimally unbalanced part. Okay? So in that case, you want to make your left subtree look like itself is like unbalanced against the other one. So this will be 2/3 of your whole size. And to add that, right, assuming that we know the final size already, the number of nodes we need to insert is just, this part is 1/3, then everything, the 1/3 is the one that you have to insert. So the one that you have to insert is just 1/3 of your new size, hence it will depend on the size. Done. Okay? But that is logically speaking. So I will show you here the solution. Thank you very much, Wang Che, for the great insight. So we can assume that if we perform the rebuild operation, right, rebuild is because there is an unbalanced child. Okay, so that means that one of the children, the size will be greater than 2/3 of the size of the total tree. Okay, so in this case, you can imagine that this is the state of the tree after the rebuild, right? For it to be imbalanced, without loss of generality, one of the subtrees should be much greater, such that the ratio becomes like 2:1. Okay, so here's how to prove it mathematically. Can bear with me first. So I will introduce some terms here. W0 would be the size of each child. Okay, W0 here. Then assuming that since it is balanced, right, then we are going to take Wang Che's assumption that both of these will be equal once they are finished rebuilding. Okay, should be roughly equal. Then we are going to add some items in the left side and some items in the right side so that it will become unbalanced. This part is general to left and right because we are taking about when will it become unbalanced. But later on we are going to take the minimum number. Okay, so in this case, we know that for an unbalanced tree, one of the child, right, should be greater than 2/3 of the size. Okay, so the size of the left subtree will be equal to the original size of the left one plus how many items you insert on the left. This should be greater than 2/3 of the size of the left subtree plus the size of the right subtree plus whatever you insert on the left plus whatever you insert on the right plus your root node. Correct? Everyone okay with the size here? Okay, this size of the two subtrees plus whatever you insert on the left, whatever you insert on the right, and the root node. Okay? Now, I can multiply 3 on left side, then I can simplify. I get L should be greater than W0 plus 2R plus 2. And this one, I can further generalize this. If I add R on both sides, then it should be L plus R greater than WO plus 3R plus 2. But this one, I actually won't be using this because my R will be positive, right? So I can say this as WO plus 1. Okay, why do I need this? Because I will need this for my second part here. Okay, so we know that this size, this one is your size just now, right? The size of your tree. Size of your tree, if I add 1, this should be lesser than. Okay? If I merge these two together, then I will get 2 times WO plus 1, merge 1, plus left plus right. And this should be equal to 2 times left plus right, plus left plus right. Okay, because I know that WO plus 1 is less than 1 L plus R, right? So this should be less than 2 times L plus R, plus L plus R. Or this would be saying that the size will be less than 3 times left plus right. Okay? See, from this part, we can already stop in this sense. Because this part is your size. This part is your number of insertions multiplied by 3. So your number of insertions should be greater than size divided by 3. Hence, we can get the minimum bound already. Okay? But this one is just for formal reasons. So we know that this is actually your insertions. Then this part is your size. So I'm assured that your insertions over size will be greater than 1 over 3. Or insertions will be greater than 1 over 3 of the size. Since we are taking the lower bound, hence we are taking this one as our omega notation. Okay? Hence, the lower bound would be dependent on size v, omega size v. Okay? Any questions? Lost. But yeah, you can follow the Wang Zhen's idea also because this one is literally the more fancy way of plating for Wang Zhen's idea. Yeah. Okay? Okay. Instead then I'll just do a faster run for this. So we want to show that the depth of any insertion is O log n. Now this one is actually easy. So anyone wanna share for this? How to show that the depth of any insertion is O log n? How to show that AVL is also O log n, something like that. Why is it O log n in the first place? Because the height of the tree itself is balanced. Because it's balanced, that's why it's O log n, right? So this is how we can prove. To prove that the depth itself is O log n, it suffices to actually show that the tree is balanced after every time you rebuild. Okay? Once your tree is balanced, then this will follow this inequality, right? That your left subtree or your right subtree, both of these, right, it should be less than equal to your 2/3 of your total size. That is the condition of balance for our scapegoat tree. Correct? Everyone agree with this? Agree? Not agree? So once you are balanced, right, you will see that none of your left or your right will exceed your 2/3. Right? So I can say that both of these should be less than equal to 2/3 of my size v, size of the root. Okay? Left subtree and right subtree, both of these should be less than equal to 2/3 of my total size. Okay, that's what it means. So to actually get the depth itself, right, I can think of it as this way. I can create a recurrence relation. For this amount of size, I can get the maximum of the left and the right subtree. That is like the maximum height. Correct? The maximum height. Now, given that they are like at the maximum position, right, in this case, it should be still less than equal to 2/3 of my whole size. If it exceeds 2/3, in that case, that will no longer be a scapegoat tree. Okay? So this part is actually my invariant, my property of a scapegoat tree. Because I know that my left and right will never exceed this invariant, hence I can take this as my upper bound. And in this case, can anyone tell me the runtime complexity of this? Runtime complexity? If I recurse 2/3 all the way, this will be log n. Okay? How do you actually get the log? Okay? You can always refer to Master's theorem. Okay? You can always refer to Master theorem. Any questions? No? Okay. No question. Then the last question here. We want to claim that the amortized cost is O log n. Now, how do we prove this? This part is actually a bit simpler. Which method can we use for this? Any suggestion? Let's try to use accounting method for this. Okay, let's try to use accounting method. So in this case, I will have like, say, one item. I will add it somewhere here. Say this will be 6. Then I will add here an 8. Then I will add another, say, 7. So my size is now 3, right? So every time I add, I will store, say, $3. Then $3. Then $3. Okay? Then I move down. Say I will add, this should be 5 lah, I think. Say 3. Then I will add another one here. Say I add 2. Then this will be also $3. I will keep. So total now I will have 3 times 4, that's $12. I will go to the right. I will keep a 4. This will be another $3. Has this exceeded my size already? Not yet, right? Actually from here already you see there. Is it? Size is 5. 2/3 is 3. Is it? About 3 point something. Okay. This one not yet exceed, I think. Okay. So moving on, I will get here say 5. This should be also $3. Okay. Now in this case, whenever I insert, right, I will store $3. $1 I will use actually to insert a note. The other $2 I will keep. Okay. Why do I keep later on? You will see later on when I have like $5, I have 5 here, then this will look, the 3 should be 6 divided by 3, 2. This should still be like, this is like currently the maximum imbalance part lah. Okay. Then if I have another one, say I add 1 here, then boom, I will need a resize. Okay. So now I will keep like $3 every time. Then every time I actually use them, to insert I will need $1, right? Now to rebuild, how many do I need? How many do I need to rebuild here? Any ideas? Ideas. So let's see. To actually rebuild, right? Rebuild, that means that I will need to use $1 to rebuild everything. Okay. Now why do I actually need $3? Because once I finish rebuilding, okay, each of my node now will store like a certain amount. Okay. Say once I finish rebuilding, then I will take $1 off, right? Okay, say suppose I will take $1 off of each here. Now why do I keep this amount? Because later on, once I proceed down, once this has been rebuilt, right, I will need to add a certain amount of nodes so that it will get another rebuild. And this amount of nodes that I add, right, at the minimum bound, that's dependent on your size fee. Okay, if you recall from the first part, the amount of nodes that you eventually add is 1/3 of your total size. Okay, hence you will have 1/3 of your size fee here. Okay, you have 1/3 of your size fee nodes. Each of them will store $3. Okay, so 1/3 of the size fee, each of them will store $3. Hence, later on, you just need to add $3 worth of 1/3 size fee nodes. This will give you your size fee. So, this amount will be equivalent to covering the rebuild of your entire tree later on. Okay? So because of your 1/3 size fee, if each node will keep $3, right, then 3 times 1/3 size fee will be just size fee. And that is already enough for rebuilding. Because one node will take one operation, so you will just take size fee. Okay? Hence, why is it log n? Because we are only adding to the depth of log n also. This part is because of the previous second question. So every node that we add, we are only adding $3. $3 multiplied by 1/3 size fee, that will give you the enough amount of money to actually do a rebuild. Then every time you add another one, then you do a rebuild. So size fee will be equal. Okay, any questions on this? No? Okay. No questions, then that'll be it for this tutorial. Thank you very much for coming. If you have any questions, feel free to ask me after the class or Telegram. Okay? That'll be it for today. Thank you very much. So for Chinche's class, only 5 of you, right, that join. Because I have to report back to Chinche on your progress. Okay, thank you very much for coming, guys. All the best.